So good afternoon, everyone. Welcome to the post-lunch session. So even she had a difficulty, pronouncing my talk, right? It's supposed to be awesome FSM. I mean, if you know me, I have a history of wordplay, right? The last year I had a talk, and it was titled "Server Less is More," right? And this year I'm using this awesome FSM. So this is my cheat code to get into PGConf India, right? Come up with catchy one-liners for the topic, and people either don't understand or they think it is cool enough to get in, right? So that's so maybe somebody else could try it next year. So this is an internals topic. I'm going to talk about FSM, which is the free space map, and I think this is an interesting feature, right? This feature talks about how Postgres has evolved. I mean, so it has been around for like 20 years now, this feature, right? And there was a certain implementation that happened those many years ago, and then Postgres became popular. Postgres started becoming enterprisey, right? So that implementation started getting issues in terms of performance and scalability, and then how the community tackled that. So I think it's a pretty interesting case study and a journey. Regarding me, if you haven't bored by looking at my face for the last 3 days, my name is Nikhil Sontakke, and I have been doing Postgres internals work for 15 plus years now. I was in EDB when it started off in Pune, and then after that, I used the liberal licensing that Postgres provides, and I did a couple of startups based on Postgres. I was in StormDB with Jim Loginski, and it got acquired by a US-based company, and after that I did another startup of my own. And post that, I have had stints in second quadrant time scale, which is now known Tiger Data, and most recently I was at Microsoft. So a hat tip to Microsoft for enabling me to submit this while I was there. There's no clicker, man. So here's the agenda for today. We'll talk about what is an FSM. Whenever we talk about Postgres, we have to talk about MVCC, right? I mean, MVCC has its pros and cons. We think it has more positives, but then the space issue is a bit of a negative, right? And the entire vacuum stuff and everything else that goes along with it, auto vacuum, that's one of the pain points. So we'll look at what is the connection of FSM related to the MVCC issue. And then we'll look at how the implementation for FSM mandated the creation of forks. And once we've understood that, we'll go down the rabbit hole and actually look at how an FSM page looks like, what are the contents, what is the layout, how free space is tracked and used in insert or update operations, and so on and so forth. I have also come up with a slide to compare the FSM implementation with other databases out there. So just to give you an idea as to how good Postgres has done a job. I mean, obviously I might be biased and I might say Postgres has gotten everything correct, but let's take a look at that as well. And as I said, I'm a developer, right? So obviously there is no official roadmap for FSM improvement as of now, as I'm aware of, but I've given my own things that we could improve in FSM. So PostgreSQL uses a file system layout for the data pages, right? You have a file system data directory. It has the base subdirectory. Then there are subdirectories for databases inside the base subdirectory, and there are relations inside that, right? Now, this is the typical problem that Postgres has to solve. It gets an insert query, and it has to decide where that insert should go into, right? So this is the question that the FSM is trying to solve in a nutshell, right? This is like the one-liner thing that given a row, where should I insert it? So before we look at other stuff, let's look at MVCC. A brief refresher. I mean, there are people in this room, who know MVCC much better than I do, but for the sake of completeness for everybody. So MVCC stands for multi-version concurrency control, and I've given a very small example here. So here you have transaction 1 and transaction 2. They both started at time t1, and let's say there is a single row in this table T. Now, when you at T2 and T4, when you run select star from T, it will see a version of the row, right? And here we see that in transaction T2 at T3, we are updating that very row. But because of the way MVCC works, at T4, when you run the select, it will still see the old content of the earlier row, right? And that happens because of this concept of snapshots. So whenever a transaction starts, it gets a list of all the active transactions that are ongoing at the same time. And obviously, any transaction which is after that snapshot in that ID value, that is obviously going to be invisible. So how does that work? It works because Postgres implements multiple versions of the row based on the MVCC semantics, right? So and for that, very briefly, there are system columns in each row. So there is the xmin column, there is the xmax column, and the xmin column contains the transaction ID of the inserting transaction, and the xmax column contains the transaction ID of the deleting transaction, right? So in this case, as you can see, the old row will have its transaction ID set to the first transaction, and in case of update, because you have multiple rows, you will have the old version and the new version, and then because of the update, the old version will have its xmax set to the transaction ID of the transaction which caused the update, right? So as might be clear from the earlier slide, there is no in-place update in Postgres, right? There are databases like Oracle which do in-place updates. So in Oracle, they have an undo relation where the old version of the row is kept, whereas the current location always points to the latest contents, right? But in our case, we create a new version of the row, we mark the old version as deleted, and then when the new transaction commits, that becomes the new content of that row, right? Okay. So as you can see, because of this dead tuple still stays in the main relation, and once the new transaction has committed, that dead tuple leads to dead space in the system. And this is like the fundamental issue that we have with MVCC, right? And that is why we have vacuum and those various settings. We have auto vacuum. We suggest good DBA practices around vacuum and everything else, right? So now that I've done a brief about MVCC, let's look at the problem again, right? So when we insert new data, we need to answer this fundamental question: where should we store that new data? The solution for that answer is we do that via FSM. So what is FSM? It is a lightweight per relation data structure that stores not exactly but approximately how much free space is available in each page in the relation, Now we have different types of pages. We have main table pages, we have index pages, right? We can have multiple indexes, right? So we'll have multiple index pages. So FSM tracks the free space in every type of a page in its data structure, right? So here as an example, we have 5 pages in the orders table, and FSM will tell you, which page has how much free data in it. And here's an important, I would say, implementation or an optimization, that FSM does not store exact bytes. It stores what is called as categories. So there are 0 to 255 categories, and I'll talk more about categories as we go along. Now, always do this, right? I mean, what could be like the brute force approach if you don't have free space map, if you have an MVCC implementation, if you have updates and deletes and inserts happening, right? So let's say you have to answer that question again, right? I have a new row, I want to put it into the table, right? What's the brute force way? Start with page 0, check whether it has space. If it doesn't, move on to the next one. If it doesn't, then move on to the next one. Check if it has enough space. There is space, but check if it has enough space. If it doesn't have enough space, then move on, right? So eventually you will find a page which has enough space for your requirements, right? So obviously, this is like a order of n kind of a scenario where you are trying to find a page, right? The other alternative is to not worry about this at all, right? But then you will have infinitely growing tables, and it will lead to other problems. With FSM, because of its representation, and I'll talk about the representation, it will just be like a log and lookup where you will ask FSM, give me a page which has that much amount of space free, and it's a binary tree structure, so it will very quickly find out where there is enough space and give you that information, right? So now you have like this pretty performant way of finding free space, because you don't want to spend a lot of time doing that, right? I mean, the databases try to optimize the IO code path, reduce the CPU contention and the computation costs, right? So we want to quickly find out this very important information as quickly as possible. Yeah, I already talked about this. So now that we know what FSM is and what MVCC causes, right? This is the typical life cycle that will happen. So an insert will happen, right? FSM will tell from where into which page to do the insertion. Once you do that insertion, that space will be utilized. So obviously you have to update the FSM to indicate that there is less space on that page. And then again MVCC, right? Update is basically a delete of the old version followed by an insert of the new version, right? Delete is just changing the Xmax to point to the deleting transaction ID, right? So all these two activities, updates and deletes, will create dead space. And we all know that vacuum is the way to reclaim that dead space. So vacuum is the one which will look at the page contents, it will look at the rows, it will look at the visibility and everything, and it will then decide whatever is the amount of space that has been reclaimed, and that will be updated into the FSM, so that next time around, the next inserts that come in, they can reuse the space efficiently. So FSM is important in that way because it is the bridge between the space reclamation activity and its actual usage for future updates and inserts, right? So yeah, let's look at, I said, this is an interesting thing, right? I mean, I wanted to see, how PostgreSQL has evolved for changing needs and requirements as it has gotten popular and more enterprisey, right? So this is a long time ago. PostgreSQL 7 was like, maybe 2007, 2008 time frame. But the first implementation of free space map, it existed as a single in-memory shared memory structure, right? So there were these two important configuration parameters, max FSM pages and max FSM relations. So the default value for max FSM pages was 20,000, meaning you could track those many. How much is that? Given 8 KB, 16 MB. That was the default, and the other parameter had a default of 1,000 relations. So you could track free space map for up to 1,000 relations in your database instance. And obviously, because it was a shared memory structure, if you wanted to make changes, you had to restart your instance, right? I mean, Ashutosh did this talk about resizing of shared memory, right? I mean, so it's like still we are still working on that, so that indicates that a lot of work is still pending in that area, right? Post the initial implementation, there was some improvement in the implementation. Proper additional vacuum integration was done. The optimization was done to store the space as efficiently as possible. But the bound was still these two parameters, FSM pages and max FSM relations. So you were still bounded, and if you had, let's say, a large number of tables, then you would not be able to track them, so obviously then you wouldn't be able to reuse the space in those tables efficiently, and so on and so forth. So these were like and as we got along, as the community got feedback from users, we realized that the 7.x, 8.x implementation had these problems, right? So the first problem I've already mentioned, right? If you wanted to change the parameters, you had to restart the cluster, which is not always a great idea. As I said, there was a single array in shared memory for the entire database instance, right? So you can imagine that all the tables from all the databases are trying to go to the same structure to get information. So that was causing a lot of contention. Because of the limited nature of these configuration parameters, you could only track so many pages and so many relations, right? So that would miss out on storing information for newer tables, and it would cause bloated and wasted space. The other important limitation was this FSM information was not persistent, right? So if you crashed, or if you wanted to change the parameters and if you had to do a restart, right, then you would lose that entire information. And then you would have to, then vacuum would have to again work hard and again repeat the same job of finding free space information. And till that time, again, you would have degraded performance, meaning you would just start putting data into the end of the table. So there was a lot of limitations, and obviously these were discovered over time, right? We had customers telling us, I can only track so many tables. I have I wanted to just do a quick change and I couldn't, or oh, I made a change and now I don't get the benefits, right? So, and the community started listening to the feedback, right? And then in 8.4 this rewrite of this feature came into play. Obviously, this is like when it got committed, the work started much earlier. And how many of you here know Heiki? Okay, so Heikki was the CTO co-founder of Neon, which got acquired by Databricks, right? And he's also a committer, right? So, yeah, I have had the good fortune of working with him as well when we were in Enterprise DB earlier. So we took feedback from the customers and the community, and this rewrite happened, right? And what happened was, from all the limitations we had, now we have a new architecture where per table you have the FSM file, which tracks the free space map at the per relation level, right? Because it's now like a regular file, post relation file, it can grow and shrink as per the PostgreSQL usage criteria. Importantly, that data is stored on disk. They are regular PostgreSQL pages. So, checkpointing, dirty pages, everything, all that applies. And, now it survives restart and it is persistent, right? And I mentioned this, right? I mean, it's a binary tree implementation, so the lookups are pretty fast. And the important thing is there are no more these kind of knobs, I mean, that's like a DBA's dream, right? There's a feature which does not require any modifications, right? So there is no max FSM pages, there is no max FSM tables anymore, right? So zero config thing. So, and it's important to note that this was done in 2009, and again, this is a testament to the way PostgreSQL works, right? I mean, things are so well thought out, right? Like even after 16, 17 years, there's not been a need to rewrite this again, right? So the community took feedback, then we came up with this this design, and it was brilliantly implemented, and we've hardly had any additional changes required for this. So now let's delve deeper down and look at what all changes were carried out. So as I mentioned, we needed a per relation table to track the free space information. And that is where this concept of forks came in handy. So when you do a create table, multiple underlying physical files get created which are mapped for that specific table, right? So there's obviously the main table. So there's the main fork where the actual data is stored, right? And this numbering is the OID. Every table gets an object ID, and typically all the files at the database file system level will be based on your OID. Right? For the main fork, you can see files numbered as the OID, OID.1, OID.2. Why do we have this in Postgres? There's the concept of a segment. So one segment is 1 GB in size. And the moment we cross 1 GB, then you automatically create the next segment, right? So this will correspond to the first GB. This will correspond to the second GB, and so on and so forth. Now, along with the main fork, there are a few other forks that get created. There is the FSM fork, and it is OID underscore FSM as the file naming convention. There is also a visibility map, which is called as OID underscore VM. And then there is an init fork. So all the different forks have different utilities. We will focus on the FSM fork here, right? So yeah, this is like, let's say you have a database with an OID 16385. If you just run an ls inside that, you will see these kind of files inside that. And if there's this function which will give you the exact result, and then you can basically get the OID and check for whether underscore FSM or underscore VM or underscore init exists or not. So that was the first thing, right? Create a separate file per relation for the free space map tracking. Now, once we have that file, let's look at, how actually it stores free space. So some time ago, I talked about the categories. So and I also mentioned that we track the space approximately, not exactly, right? So the granularity that we track the free space is at 32 bytes. So which means that 8 KB divided by 32, you have 256 categories, right? So if your slot has a value of 0 per page, then it means that the page is full, right? If it has a value of 128, so 128 into 32 bytes, right, which is roughly 4 KB. So it has 50% free space. And obviously, if it is 255, then it means like it's completely free. And that can happen when you've done a bulk delete, where you have wiped off data completely from a table, and then vacuum has ran. So then vacuum has updated that information saying that this is a 255 category page, right? In terms of the page layout, as I said, it's a standard PostgreSQL page. So it's a 8 KB page in size. Because it's a standard page, it has to have the standard page header. So information like which LSN updated this page last, and if you've enabled checksum, then the value of that checksum, and all other flags that you have, the pointers to the free space and everything, all those are present there. For FSM pages, there's this specific field, FP next slot. It is an optimization that has been done. I'll also talk about that later. It will be much clearer visibly when I get to the actual layouts in some cases. Then, as I said, it's a binary tree node. So you will start with the root node, and then you will have internal left-right trees. And eventually, at the leaf, you will have the heap pages with their corresponding space information, right? So you'll have at the lowermost leaf level, you'll have the free space. So as I said, we don't store exact bytes, we store category, right? So we'll have the category from 0 to 255 to indicate the amount of free space, approximate free space. And with this layout, we can understand that one page can hold up to 2K heap pages, right? And because it can hold 2K heap pages, 2K into 8 KB is 16 MB, right? So it means that one FSM page can approximately point to 16 MB worth of space in a given relation, right? Which means that once that page grows beyond 16 MB, then you will have the second page added into the FSM, which will point to the next 16 MB. And that ways you can continue. So let's look at a sample example of an FSM page, right? So as I said, it's a binary tree. So you will start with the root. You'll have the left and the right child, and then eventually you'll have the leaf nodes. And here you can see, for every node, we know which category of space it has free, right? So in case we have to answer a query like I need space up to 150. So you can start off with the root. You can look at the left and the right trees, and then you can eventually drill down to the left portion and return that P1 has enough space to satisfy your space requirement. And obviously this is like a standard B tree structure, right? So you will reach to your location pretty fast. So then the question next that you can have in your head is what to do with very large tables, right? I mean, obviously PostgreSQL caters to very, very large tables, right? The answer to that is there are like multi-level FSM trees. So instead of the internal nodes directly pointing to the leaf nodes, they point to FSM pages and there can be as much leveling needed as required, and eventually the last FSM level page will point to the leaf pages, right? So as you can see here, this is the level 2 page, which is the root page. It will point to individual FSM pages, which will then contain 2K pages worth of information, right? And basically every the summary will be like the max summary from every underlying page. We'll take a look at the example as well. So because of this, now you know that one level corresponds to like 16 MB. If you have 2 levels worth of FSM, it will correspond to roughly up to 32 GB in size, right? And with 3 levels, it can grow up pretty large, taking care of like a very large kind of a table. Okay, so a simple demo to look at how things work. So I created a demo table. Now if you do an ls, you will see that only the main fork exists. There is no FSM file yet, and Postgres, like tries to optimize everywhere, right? The brute force would have been just create all the files together, but we do it only when it's needed, right? What if there's an empty table which doesn't get used? There's no need to use an inode at the file system level, right? And typically, this file gets created when you run vacuum or auto vacuum, or there are cases where you have done enough inserts, and if you are doing an inline pruning of dead space for whatever reason, right? So like let's say you're doing a sequential scan, and while doing the sequential scan, the backend realizes that there's a lot of dead space that can be reclaimed. So it does like a sort of a mini vacuum, like doing a update of the FSM, and in that case, if the FSM doesn't exist, it will create it on the fly. But most use cases, vacuum is the one where you will actually end up creating it if it does not exist. And here is this extension called as PG free space. It's a contrib extension, so you can install that, and you can inspect the contents of the free space map to give you a fair idea as to So here I've just shown an insert, but obviously you have to do some updates and deletes as well to get some FSM information going. If you have only inserts, then none of the pages will have free space unless you have used fill factor, where it will keep some free space around. So let's say this is like page 4 pages, and it has so instead of storing the bytes, FSM, while storing it, calculates the category, basically division by 32, and get the corresponding FSM information set up there. And this is how then once you have gathered that information from vacuum, so vacuum will give information of this kind, right? Page 1 has 7,500 bytes free. Page 1 has 3,000 bytes, page 2 has 0 bytes, and so on and so forth. This information is given to the FSM update code path, and that is the one which converts this bytes into categories, and what gets stored into the FSM is the categories. And in this binary structure, the internal nodes store the maximum storage from the underlying leaf nodes. Like in this case, you have 234 and 96, so the internal leaf node will contain 234. In this case, 255. And the maximum free value will get bubbled up from the underlying levels to the topmost level. So now if you look at the root, 255 is the maximum, the value which represents the maximum free space available in any heap page in that table, right? Now let's do a delete from that table, right? And so you did a delete, you removed a bunch of rows, and obviously you want vacuum to do its activity. And so let's say before delete, this was the categorization, and after delete, this is the categorization. Again, this information is sent to the FSM, and it will update the leaf nodes first and then bubble up the information. So now, as you can see, even the left side has enough space, and the root will indicate that there is space there. And once this information has been set up, all the subsequent inserts will consult the FSM and get existing pages to use for the spaces. So again, a simple example, let's say your FSM is populated and you say insert values. So you have the tuple size that you need for your row. You will convert that into a category, right? So 200 divided by 32, rough your approximate category. And you will start from the root node, check the value, yes, there is space, left or right. Again, there is an optimization about FP next slot. I'll talk about that later. It will eventually go to the leaf node, and the leaf node will give us the heap page number into which the insert can happen. Right. The important thing here is says, it says try to insert into that heap page, and we'll see why it says try to. Right. And yeah, the same. Once you've returned a page, if there is successful insert into that, you also need to update the FSM. So you need to propagate the changes again from the bottom up, right? You modify the leaf node, then you modify the sub parent until you actually reach up to the root node. And now, because this is a binary tree, maximum you need 10 to 11 node updates, right? So the changes will bubble up pretty efficiently, and you don't have to touch any other existing nodes in the system. So it's possible that the FSM gives you some information and gives you a page to insert into, but the heap insert actually tries to use that page, but it somehow ends up finding that there is not enough space in that specific page, right? So Postgres treats FSM as a hint structure. It's not like the accurate source of truth for about free space, and so whenever it gets a miss, it actually goes and retries with another page. In terms of optimizations, as of now, the category is like up to the value of 255, so it can be stored sufficiently in 1 byte. There was an option to store it in 2 bytes, but it's maybe more unnecessary, and most of the times just using the approximate category is good enough for the most common use cases. Most importantly, it also reduces the wall for FSM updates, right? So there's this wall amplification that happens with inserts and everything, right? And we want to minimize that as well. So if you use this category, then it reduces the that usage as well. Obviously, it's cache friendly as well. You can fit in more data in the cache line, and more leaf nodes will also fit in the space. I was mentioning this optimization about FP next slot, right? So the way without this, what would happen is like if you keep on asking the query where is data, it would typically find the page which is leftmost and return that every time, right? So that can cause a lot of hot spotting on specific pages, right? I mean, if you have 10 backends trying to insert into that table and we return that same page to all 10 of them, then it becomes a problem, right? So the idea is to spread the load evenly across the different pages, and that is where this FP next slot optimization is used. So every time you will do like a round robin calculation typically you will do like a mod operation, and it will identify the next page every next time you do the insert operation. So that allows for concurrency and spreading of I/O across different pages. Yeah. Besides, I think I need to be a little faster. We are running out of time. So apart from this, there is the hot update, in which case you can consult the FSM to ask whether there is space in that same page or not, right? And sometimes, when you're doing sequential scans, if you see that there are a lot of dead tuples in a page, then you could immediately update the FSM without waiting for a vacuum. I think let me not spend too much time on this. So I took some time to look at how others have implemented this. But I mean, if you look at PostgreSQL, it's like the best implementation. The other heavyweights also seem to have a lot of limitations in terms of the granularity of the tracking of free space, and what is the, whether it's per relation or database wide, and contentions and all other factors. So if you look at it, PostgreSQL is coming up trumps, which again talks about the enterprise rock solid quality of the implementation that we have. Yeah. Extensions, there's free space map, and there is I'll be uploading my slides, so if you want to use the this for like estimation of bloat and find pages which have been missed by vacuum. Page inspect is another contrib module. You all know about that. Yeah, here is like a a easy way to check how the FSM is changing. Yeah. In terms of parameters, it's like the usual auto vacuum, but nothing specifically needs to be done for FSM. All the rules that apply for efficient vacuum typically tend to allow apply for FSM. So for write heavy tables, you should set the scale factor a little lower so that you can have frequent FSM vacuuming happening. And yeah, if you have hot updates, then obviously you should use a fill factor of 70 so that you can quickly consult the local FSM when you are doing the updates to do a hot update. Yeah, I think just wanted to quickly close by talking about future enhancements. I mean, this comes from my time scale, right? So there's like a lot of IoT data where like there's or time series kind of workloads where there's a lot less number of changes that are happening. You could always have a head pointer to skip the initial full pages, and then only track the changes that are needed later on. So this could be like pretty fast. You can always skip those pages in one shot and then look at the new pages. This is also interesting. You can do run length encoding compression for FSM. So if the range of pages are full, instead of having the tree structure, you can just mention that pages 0 to 10,000 are full. So you can just have one single entry instead of 10,000 or entries, right? And this could be really useful for append mostly kind of tables which have been clustered recently, right? So there's like not much bloat there, and obviously read heavy tables with rare deletes, right? So there you don't want to like look up the FSM unnecessarily most of the times, right? So this could be an interesting optimization that could be done. This is also interesting, FSM aware query planner. We could get better table size estimates, right? I mean, right now we just look at the size, overall size of the relation. But if FSM tells us that there is like 30% effective free space, then we could have better sequential scan cost estimates, right? There could be better vacuum coordination. FSM could look at pages and say, hey, there are these pages, which might need urgent vacuuming, right? So vacuum could use that as a hint and start looking at them first before looking at in a specific order or things like that. And again, now that we have async IO and stuff, the third point might be interesting as well. If we could consult FSM and it could tell us which pages have free space in them, right? And if that table is insert or update heavy, then it would need that free space much more frequently, which means instead of doing the I/O at that time of the update or the insert, we could prefetch those pages, put them in shared buffers before the request for them comes in. So this could be a pretty useful optimization as well. Okay, I think this is all. We're done with time, right? Okay, yeah. So yeah, this is the references. Again, thanks to Heki, and